365 days. 1 year. That's how long it takes for the Earth to complete one revolution of the Sun, one orbit. We all know this. We all know that the planets orbit the Sun. But how do we know? Who discovered this? And how can we predict the movements of the planets? Like much of modern science, the first inklings of heliocentrism came from Greek, Chinese and Islamic astronomers. But it wasn't until Copernicus in the Renaissance that the idea became more well known. Johannes Kepler, a German astronomer who studied under Tycho Brahe, followed in Copernicus' footsteps to prove that the planets did in fact orbit the Sun. He also improved upon the Copernican Model to describe Mars's orbit, which didn't fit the original model as it described orbits as being perfectly circular, which Mars's definitely isn't. Kepler showed that the planets orbit not in perfect circles, but have slightly elliptical orbits, with the Sun at one focus. This was his first law. Kepler's second law elaborates on the first, by saying how the speed of an orbiting planet changes depending on where in its elliptical orbit it is. It reads, "A line joining a planet and the Sun sweeps out equal areas during equal intervals of time." But what does that mean? If we were to draw the orbit of a planet, say Mars, then you can draw an ellipse with the Sun at one focus, like this. Obviously not to scale though. In the 100 days it takes to travel this far in its orbit, it has swept out this area, A1. Half a year or so later, when it's further from the Sun, it takes the same amount of time to cover a shorter distance. But if we actually draw out the area it's covered, the section is longer, so the areas are actually equal. This is essentially Kepler's second law, and translates into what we see in real life. The closer you are to the Sun, or any gravitationally large body, the faster you travel, which allows us to get around the solar system more quickly using slingshot manoeuvres. The point furthest from the Sun in an orbit is called aphelion, and the closest point is perihelion. The more eccentric or elliptical the orbit, the greater the difference in speed between the 2 points. The most eccentric or least circular planets in our solar system are Mars, Mercury and Pluto if we're counting it. Its eccentricity is actually one of the reasons for its demotion to dwarf planets. The final law is an equation that links the period, or the time taken for the planet to complete one orbit, with the semi-major axis, or the distance of the Sun to the planet. Kepler found that these two values, with a bit of manipulation, were directly proportional. This means that if you drew a graph of a cubed against t squared, then you get a straight line. The gradient of this line is the constant of proportionality, which is essentially what you have to multiply t squared by to find a cubed. Kepler found this constant to be, roughly, 7.5 times 10 to the minus 6 astronomical units cubed per days squared. He did this by dividing the radius in astronomical units by the period in days. This might seem like weird units. Well, it is weird units, but you've got to remember that back then they hadn't found a way to measure the actual distance of the planets from the Sun. They could only measure it in comparison to the distance between the Earth and the Sun. So they would set the distance between the Earth and the Sun to be 1 astronomical unit, and then they do some fun trigonometry to figure out the comparative distance. This unit actually is still used a lot today, and it's turned out to be really useful. So, Kepler discovered the relationship, but it wasn't until Newton, who 80 years later proved the laws mathematically using his laws of motion and gravitation, that we got the neat formula that we use today. Let's take a look at how he did it. The original third law, as written by Kepler, was expressed mathematically as a cubed equals kt squared, where k was the value he found experimentally. But he didn't know what this value actually meant, which is where Newton comes in. If we take his law of gravity, which describes the gravitational force between two bodies, and the equation for centripetal force, which is the inwards force creating circular motion and comes from his second law of motion, then we can find where the constant comes from. For an orbiting planet, the inwards force pulling it into a circle is the force of gravity, so we can equal these two equations to each other. The law of gravitation is force equals g, the gravitational constant, times the mass of the star times the mass of the planet, all over the distance between each object and the centre of mass added together. As the centre of mass is very close or even inside the Sun, we can get rid of our star and take this as equal to the radius of the planet's orbit. This makes simplifying the equation so much easier. If we equal the two formulae together, we can quickly cancel out the mass of the planet and get rid of the radius on one side, leaving just the planet's speed squared on the right-hand side. We can then rearrange this to make the leftover radius the subject of the formula. At this point we have to bring in a third equation, but don't worry, as it's just the simple speed equation with some fancy words. The time taken for one orbit is the period, and the distance travelled is just the circumference of the orbit. Rearrange this to find the speed or velocity of the planet, Vp, then we go back to our earlier equation and replace Vp with our new formula. I find it easier to do this if I separate the fraction out instead of having fraction over fractions, then flipping the second one and multiplying them together, but don't forget that the second fraction is squared. We still have Rp on both sides, but we can just times this up, and then we can separate the right hand side into a constant and p squared, and voila, Kepler's law. You can quickly rearrange this depending on which variable you want to find, and now we know where the constant k comes from and what it means. I've used different letters to Kepler's law, which could be confusing, sorry about that, but I've written it out more clearly here. And that's it, we've just proved Kepler's third law mathematically. If we look at the constant, we can see that part of it is just a value. Pi will always be pi, and g is the universal gravitational constant. It will be the same anywhere in the universe. But multiplying by m star means that the constant changes between systems. For any planet orbiting the Sun, that system will be, well, constant. But if we look at the orbiting moons of Jupiter, the constant will be different, as you multiply not by the mass of the Sun, but the mass of Jupiter. Let's check it for the planets. We can make it really easy for ourselves if we measure t in Earth years and a in astronomical units. As when we sub these values into the equation, you find that k must be equal to 1. So for our solar system, measuring in these specific units, a cubed actually equals t squared. This is more of a Keplerian way of thinking about it or testing it than a mathematical or Newtonian, but it does work. But Jade, didn't you say that Kepler got a different value? Well, good listening. Kepler actually measured t in days, not years, so it's a slightly different equation. But it's easy to figure out his method, and I've done it here in purple pen. Thankfully, it is accurate. You don't have to observe the movements of the planets yourself to check it's correct. You can simply Google the values and then check using our equation of a cubed equals t squared by subbing in the values for a planet. I've chosen Jupiter for my calculations here. If the two sides end up roughly equal, you can see that it's true. I definitely recommend trying this all out for yourself. Even after I'd watched videos and read through websites to learn this, deriving the equations from just those 3 simple formulae was amazing, and the feeling when the calculator showed the two values for Jupiter were equal was pure happiness. So pick a planet and try it for yourself. Kepler's laws are so useful and have helped form or become a part of so many of the equations we use today in astronomy. So it's safe to say Kepler was a pretty cool guy, if we gloss over the fact that he may or may not have murdered his mentor, but that's a story for another day. Thanks for watching, I hope you found this interesting. Let me know in the comments if you have any questions or if I could have explained something more clearly, and make sure to give this video a like. Stay curious and see you next time!